I was being like, oh, I'm gonna spend like my whole day like doing homework and it's gonna be great. I'm gonna get so much stuff done. And then that day comes and I'm like, I'm so lazy.
I wish I had to.
So today I want to finish up a few other slides we didn't do last time, which was a calculation of activity coefficient. So I'm going to go through that, walk you through that, because that's part of the homework. And then we'll go on to the next topic, which has to do with solution chemistry. And mostly today we'll focus on acids and bases. We'll talk about some other solubility stuff, and then we'll pick that up next time. So this was, like I say, from the end of last time I had said, why don't we calculate the true activity of calcium ions in a 0.05 molar solution of calcium chloride. Remember, activity and activity is not predicted by thermodynamic theory. They are basically non-ideality corrections in the case of aqueous solutes that are charged. So we can't apply the Pi-Hookel to everything, but we can apply it to this. And so there's kind of two steps. And the first step is to calculate the ionic strength. Remember, that was basically the sum of all the moles of charges in solution divided by 2 to take into account the plus and minus charges. So since the charges go in here squared, right, all the charges always turn out as positive. That's why we have a 0.5. So we take the sum of the molality times the charges, and I've just pulled it in here. We put a 0.05 molar solution. So that's where this 0.05 for the calcium ions comes from. Plus calcium are 2 plus charges, so it's 2 squared, right? So that's what this term in blue, it follows from this thing. And then when we go to our chloride ions, the molality, right? It might seem like a, you have to think through it for a second, but the molality is 0.1, because 1 mole of this dissolves to make 2 moles of that. So it's a 0.05 molar solution of calcium chloride. It means we get 0.1 moles of chloride. That's why that's a 0.1. And then it's got a charge of 1, which is squared, right? So we sum those things up. We take half of the sum. We come up with a value of 0.15. So the ionic strength of that solution, 0.15. And if you recall from last time, we said values around 0.1 are like typical river water. So you might think, well, there isn't that much non-ideality in this solution. But according to what the Pi-Hookel theory predicts, there's a fair amount. So there's a couple of different equations, right? There's the Truesdell-Jones equation, there's the Davies equation. The one I'm working through here is the Truesdell-Jones equation. So there's basically minus log of calcium equals a bunch of stuff. There's a constant there that we pull out of the table. There's a constant there that we pull out of the table. Right, and so this 0.5085 is, excuse me, the constant is here. 0.5085 is this constant, and this constant for the value of B times 10 to the minus 8 comes from here. Okay, and it's because I looked over on the table, I found the ion that I was interested in. The different ions have different values for these constants. Remember, this is a parameterization. So this is the equation down here, right? So we're popping in an A. We're popping in a B, we know our charge squared, and we know our ionic strength, which is going into the square root, okay? And we also have to have a value for the AA, which is basically the size of the ion, right? And so that's where the 6 comes from. It's times 10 to the 8th. You have to remember to put in the 10 to the 8th of it, okay? And so you solve for all that stuff, you come with an activity coefficient of 0.0357, which says that only 35.7% of the calcium ions that we put in solution are behaving like they're present, right? That's what this activity calculation tells us. The other, something like 2/3 of them are doing something else. They're involved in ion pairs. And so that would tell us that the activity of calcium is a lot lower than the 0.05 molar, just in that solution of pure calcium. And part of the reason the value is so low is because it's a +2 charged ion. If we had a +3 charged ion, the activity would get even lower. So it's kind of a good thing to remember sort of offhand that your +1 charged ions are going to have, or minus one charged ions are going to have some kind of activity value that, is somewhat lower than the molality. But when we get into +2 and +3 and +4, that's where the ions really start to predict, at least, that they're going to be a lot lower. So then you could say, well, okay, so what quantitative effect does ionic strength have on overall solubility, right? So solubility is just a measure of the moles of something we can stick into a volume of water. For instance, the moles per liter. A high solubility chemical is when we can put a lot of stuff in solution. A low solubility chemical is when we can't put very much. So we can calculate a solubility product for the dissolution of the calcium chloride. And remember, we don't put solids in our aqueous equilibrium constants. The solubility product, and the reason it's called a solubility product is that it's just products of the ions that are produced in the solution. It's not divided by the reactants, because the reactants in this case are solid. So it's the molality of calcium squared, or excuse me, calcium 2 plus and chloride minus squared, right? Now we can also write out the expression for what would it be if we include the ionic activity. Okay, the actual values predicted that we just calculated through Truesdale-Jones. The only difference between these two things is in this case we put in the true molality as predicted from us weighing out the amount of calcium chloride on a scale, and this is the amount that's actually present in solution in a free form. Based on the activity coefficient calculation. And you can do some fancy algebra to basically show you that the difference between those two things is essentially just the product of the activity coefficients to their stoichiometric coefficients, right? So one of the equations that the equilibrium constant itself just has the molalities, and the ion activity one has the non-ideality coefficients in there as well. And so the difference is a factor of about 5. So what that tells us is that in this particular solution, you can put a lot more calcium chloride than we would have predicted if the ions were not ideal, right? And so you have to think about that a little bit, but places where this starts to matter a lot are, for instance, in seawater, if we have sparingly soluble elements, their solubility, their effective solubility can be higher than we would have thought, because of the kinds of interactions that the Bi-Hugel tries to take account for, which is things like ion pairing, etc. So does that make sense to everyone? For questions about how I did the calculation?
Wait, are you able to go back a slide or two? Let's see.
This one? This one?
Yeah, I think this one. Wait, I'm sorry. What are the bottom values?
This is the parameters that are used in the equation. So that's
or
the
like on the equation where there's like the negative log. What's
Yeah.
like the bottom value? I'm like trying to figure out what 0.3281 times 10 to the
Yeah, it's this value here, B.
Oh,
Right? And so the column here, B, 0.3281.
oh, okay. Oh, I see. Okay. Sorry, it was like so small. on the
No, that's
bottom. I was
okay.
like, wait, what?
And if you use the other equation, the Davies equation, it's got slightly different formulation and slightly different values in there.
I see.
So these equations work plus minus, better or worse in some settings than in other settings.
And so there's a negative A for that because there's a negative log on this side. So I guess like there's negative log here,
Yeah.
but on here, the negative.
It's written out slightly differently. I just moved the negative over
Okay.
there. This is a
Okay.
slightly different formulation.
Okay.
So this is just kind of a summary of that, which is that when we look at gamma, the activity coefficient, which is telling us the fraction of stuff that's present, and when we go from a typical river value of like 0.1 or 0.15 or so, depending on the river, up to a typical seawater value, which is 0.7, we're going to see a much higher fraction of our element being involved in things other than being a free ion. So its gamma is going to increase. You can kind of convince yourself of that by looking at all the different parameterizations, equations for the Bi-Hugel, and seeing how I plays a role in there. The higher the I, the ionic strength, the basically smaller the gamma. That is the only thing that affects gamma. The relative charge on these ions also affects it. So that what you find, if you just go through the math, is that for most singly charged ions, this is approximate, this is like a rough approximation, but they're basically non-ideality factors about 10%. Right? You know, it's like mostly there the way it is, but when you get up to doubly charged ions, it becomes a lot higher over this range of i's. So, you know, if you were to calculate out values at 0.1 and then again 0.7, you look at how things change, that's the amount of change that they have. So I just want to make sure I went through that calculation. You can go back and look at, there's some diagrams in the text. There's also a diagram in the lecture notes from last time that looks at these variations that derive from all three of the main equations by Huckel, Truesdell-Jones, and Davies, and you can see how they're different. And they do differ at really high I. So if we were like looking at, you know, solubility, for instance, from a ore minerals perspective in geothermal fluids at very high temperature and pressure and salinity content, then we would need to investigate very carefully whether or not one or another of those equations was working for us. So for this week, at least for the first couple times, we'll see how far we get. I want to talk about some more stuff that has to do with how things dissolve in water. That's going to be the basis of you know, a lot of the chemistry that we talked about in the hydrologic cycle. The first topic is acids and bases. And then the next topic, which we'll probably just start on today after we talk about this, is the solubility of other elements, and especially complexes and chelation, and how we quantify solubility and something that we call the total dissolved solids, or TDS, which is a common water quality parameter. So everyone, I assume, remembers what pH is, minus log of the hydrogen ions in solution. Now, accounting for the fact about non-ideality, we would actually say minus the activity of hydrogen ions. Hydrogen ions, just like every other cation solution, has an activity coefficient for it. Hydrogen ions tend to be very, very small, and so their activity coefficients tend to not make a huge impact on the pH, because it's a singly charged, very small ion, but even still, it does have a little effect. Then there's Bronsted-Lowry acidity. That's the standard hydrogen ions, hydroxide ions type of acid that you learned about sometime in the past. And then there's Lewis acids and bases, which I mentioned before. We're going to talk about a little bit more detail now. This is a broader definition of acidity. Something that's a Lewis acid is deficient in electrons. Something that's a Lewis base has an excess of electrons, so that its interaction with, especially in aqueous solutions, is to promote the conditions of Bronsted-Lowry acidity when we stick things into solution. We'll see how that works. Once we'll talk about that a little bit and what controls things at the level of the variations in the periodic chart, then we'll talk about some other ions in aqueous solution, especially with respect to charge and solubility. So, as I just said, Bronsted acids and bases contain hydrogen ions and hydroxide ions, respectively. When we get to Lewis acids and bases, a Lewis acid is electron deficient and a Lewis base is electron excessive. And this is where your Lewis dot structures are useful too. So you can think about Bronsted acids in the context of Lewis acids, right? And not vice versa. This is just a broader definition. Because if you think about it, a hydrogen ion, which is a Bronsted acid, is also a Lewis acid because a hydrogen ion is electron deficient. It's like a hydrogen atom that's missing an electron. And a Bronsted base is electron excessive. A hydroxyl Lewis base, a Bronsted base is basically water missing a hydrogen ion, right? And so that when the water split, it left behind a little bit of extra charge on that OH minus, and so it can be thought of as a Lewis base as well. Does that an explanation make sense to everyone? Okay, so you could call everything a Lewis acid or Lewis base. That's the kind of, you're always safe with that. But since most people learn about acidity with the Bronsted method, and because it's very intuitive, I like to kind of go back and forth. And what we'll talk about a little bit is how we can take chemicals that are Lewis acids and bases that don't have these things on them, obviously, and see how they create those things when we stick them in the water, and so that they have those effects. So remember, there's a distinction between what we call a strong acid or base and a weak acid or base. And it's not binary, it's a gradient, but something that's a strong acid or base completely dissociates when we stick it in water, right? So if this were a solid, it would be something with a high solubility product, something that is really soluble, that dissociates. And so HCl, hydrochloric acid, sodium hydroxide, these are things that, even though this one comes as a solid when you find it like without water, this one comes as a gas, right? So you would get it in a gas form. If you were to dissolve it into water, then it's going to dissociate this way. And I haven't put the little AQs, the aqueuses after those, but these are all aqueous. And we get none of this left, right? Basically, every bit that we put in here dissociates up to some very high amount. You can saturate the solution and get it to the point where it can take no more. But pretty much every molecule that dissolves breaks apart. So that's why we call it a strong acid or strong base. Now, weak acid or weak base is one where the equation doesn't progress very far, right? And water is a great example of it's a weak acid, because when we stick water into water, it dissociates into hydrogen ions and hydroxyl ions. What's weird about it is that not only is it a weak acid, it's also a weak base, right? Because those are the two constituents of Bronsted acidity and basicity. So it's still a neutral solution from the perspective of, does it have an excess of these or an excess of those, right? And we know that a solution that has an excess of these is acidic. That's what we call a solution that has an excess of hydrogen ions. And a solution that's got an excess of hydroxyl ions, we call a base, right? But water itself has an equal amount of both of these two things, so it's neutral. We'll talk about how we define that in pH in a second. But water is a weak acid and a weak base, and this contributes to its ability to solubilize other stuff. Okay, so there's an equilibrium constant, K, sometimes given a little W for a subscript that just means the equilibrium constant of water, which measures that dissociation, right? And it's the activity of hydrogen ions and hydroxyl ions. And it happens to be 10 to the minus 14 at 25 degrees C. So basically what that tells us is that a very small amount of hydrogen ions and hydroxyl ions are formed and are present in pure water at 25 degrees C. You do the math on that and see that the amount of these and these have to be equal to each other, right? So if we just say Kw, which is this value, equals x squared, and we take the square root, it's 10 to the minus 7. So it's 1/10 of a millionth of a mole of hydrogen ions will come from a mole of water. It's not very much, right? It's like a tiny, tiny little bit, okay? Now, it turns out that this equilibrium constant isn't constant with temperature. So if you turn the temperature up, you get more dissociation. Turn the temperature down, you get less dissociation. The minus exponent in the log goes down with temperature and goes up with increasing temperature. And so you can kind of go through the math in your head and see that you will have more dissociation, more forward progress in the reactions written at high temperature. And at 100 degrees C, it's a little bit more. And if we were to put some pressure on the system and go down, like deep into the crust, into a geothermal system, we'd get even more. It's still a small number. I mean, let's be honest. At neutral balance between hydrogen ions and hydroxyl ions, there aren't very many of them in solution. Just a few. So the other thing to remember is that this is for a neutral solution, meaning it's got, and a neutral solution means it's got equal amounts of these two things in it. When it becomes acid or base, then all bets are off. We calculate the relative amount of one if we know the amount of the other, like for instance, we've measured it, or we use a parameter called pH, which helps us define that. pH is just the minus log of the hydrogen ion concentration, which comes from taking the minus log of this equation in solving for hydrogen ions. So I'll go through that solution in a second, but I just want you to remember that the standard equation that we see where we say pH plus POH equals 14 only applies at 25 degrees C. The 14 comes from that. If we were making a calculation at 60 degrees C, the sum of the two would equal 13. So I've basically done that solution for you here, where we take the equilibrium constant of water, we do a tiny bit of algebra, right? We say the hydrogen ion concentration equals X. Since the hydrogen ion concentration has to equal the hydroxide ion concentration in neutral water, that hydroxyl also equals X. So we plug those things in, X squared equals 10 to the minus 14, therefore X equals 10 to the minus 7. Okay, that's all. I just, simple algebra using this expression. We want to take the pH, which is basically the minus log of the hydrogen ion concentration, right? I've written out the expression here. It's the minus log of the activity of the hydrogen ion concentration, which is approximately the minus log of the hydrogen ion concentration without taking into account the activity coefficient. Because remember, we've got a really, really small concentration of hydrogen ions here. The activity coefficient gets very close to being 1, except under extreme conditions, which we're not going to really talk about. Then pH equals minus log of 10 to the minus 7, the value that we explored here at neutral pH at 25 degrees C. And remember, this 14 that's here comes from this fact right here. At 25 degrees C, it's 10 to the minus 14. Okay, so you can also calculate a POH, which is just the minus log of the activity of the hydroxide ion concentration, which is also going to be 7 in this situation. And I'm sure somewhere in the past you've remembered pH equals 7 is neutral. And that is totally true at 25 degrees C. But if we did the same exact calculation at 60 degrees C, then neutral would be 6.5, would be 6.5, would be half of this value. Or if we did it at 0 degrees C, it'd be closer to 7.5. So again, it's not a huge variation, but it's something to be aware of, that the actual value that we call neutral pH does depend on temperature. Okay, so that's a neutral solution with equal amounts of hydroxide ions and hydrogen ions. But if we go in a solution that has where these two values are not equal to each other, right? We call it acidic if the hydrogen ion concentration is greater than hydroxide. We call it basic if vice versa. So this is a plot showing you kind of ranges of natural pHs that we find in the environment, as well as some other kind of common household chemicals. We're going to talk a little bit about how this happens in the hydrologic cycle at some point, but you'll see here that the range of normal precipitation is acidic. It's straddling 6. The range of stream pH straddles 7. Can anyone think why might rain be a little bit more acidic than stream water that's running off the lane? Yeah.
CO2?
Totally, that's exactly right. Carbon dioxide is an acid, it's in our atmosphere. And so when it dissolves in water, it makes the water a little bit acidic. And we'll talk a little bit about how this shift comes from the interaction of rainwater with silicate materials in the Earth's crust, especially within soils and sediments, which tend to do a little bit of neutralization. Okay, turns out that dissolving silicate minerals contributes a little bit of base to solution, so it pushes us up a little bit in this direction. And in fact, when we go into the seawater, we can see here it's about 8.2, happens to have about the same pH as baking soda in water. And that is, again, it's a culmination of processes that continue as water runs through the landscape and accumulates in the ocean, plus the added effect of having calcium carbonate solubility, calcium carbonate being something that a lot of marine organisms make their shells out of. And that also starts to tweak the system a little bit. So as water progresses through the hydrologic cycle from the atmosphere to the land and into the ocean, the pH goes up. That's kind of the key thing. And as I say, we'll talk a lot about how that happens. Now, you also see something on here. You see acidic conditions and you see acid rain. Acid rain, which is something you may or may not have heard about, has a pH less than 5 on this chart. It's actually 4.8. It has a pH that is lower that can be made by dissolving carbon dioxide in water. It needs some other kind of acid, a stronger acid. Those acids tend to be sulfuric acid and nitric acid, which come from human activities. This is one of those things where it's really hard for us to find natural range pH on the planet anymore, or places that we think were in unperturbed values, because the kinds of human activities that put nitric acid or nitric acid precursor chemicals and sulfuric acid precursor chemicals into the atmosphere are primarily burning of fossil fuel or burning of wood. So, and we've been burning wood, for probably 20,000, 30,000 years as humans. And so those activities contribute to making lower pH, which is, if you can think about, in the grand scheme of things, as water interacts with the landscape, turns into stream water, and then eventually goes into the ocean, we're going to neutralize that water either way, right? The oceans have not really changed their acidity with time. They've changed by a very, very tiny bit. And so it basically just accelerates the rate at which water that hits the landscape can weather the rocks and therefore become a little bit more acidic. And as I say, we'll talk about this coming up next time. But once we get below this pH, the pH that's naturally regulated by carbon dioxide, that's where we start to see ecological impacts. Because organisms, ourselves included, our blood is also saturated in carbon dioxide, right? We breathe in oxygen and breathe out CO2-rich vapor, and the transition happens in our lungs and is carried by our blood. And you will find this to be the case across much of the biosphere, is that organisms like to exist in an environment that is buffered in the CO2 buffer, which is what we're going to look at next because of that. It's not to say you can't find organisms that naturally exist in lower pHs, you do, but it's less common. Okay, it's more common to find these kinds of conditions because these conditions where pH is less than 5 or so are pretty rare at the surface of the earth. They exist, but they're rare, naturally speaking. They're becoming less rare, again, due to human activities, but the places that we tend to find really low pHs are, for instance, associated with volcanic emissions. So think about those very colorful lakes that you see at Yellowstone, or think about fumarole gases coming out at Kilauea, or think about geothermal waters, in various places where geothermal is utilized. Those values tend to have, those waters tend to have much lower pH because they're interacting with a strong mineral acid, usually SO3 gas, sulfur trioxide, which dissolves in water to make hydrogen sulfide. And there are organisms that have adapted to live in those environments. They're microorganisms for the most part, but we find them, but that's kind of a special case. So it's kind of useful to remember why water has the pH that it has and what some of the simple controls are from an acid-base perspective. And so that's what we're going to go through after we talk about Lewis acids. So these are the two classic Lewis acids and bases that people are generally taught about if you've had an inorganic chemistry class where they go into detail about this: boron, trifluoride, and ammonia. So it's useful to go back to the periodic chart and look where boron is. It's sitting up here, right, in group 3, and it comes with 3 valence electrons. So if you were to write out a Lewis dot structure for it, you can make BH3 or BF3 or BCl3, because basically boron has 3 electrons and you can park 3 other electrons to make 3 bonds around it, pretty simply, but that leaves a hole at the, that leaves only 6 electrons around boron, whereas a full valence shell would have 8. So whereas you can make this stuff as a gas, once you stick it in water, it's going to want to try and neutralize or accommodate that gap in its Lewis structure. It's going to pull other electrons to it so that it can become hexacoordinated. It can have 4 things around it. So BF3 will react with water to basically take an OH minus from water, right, to make BF3OH, right? Remember, water is just a bunch of H pluses and OH minuses together. If it sucks up one of the OH minuses, it leaves behind a hydrogen. Right, so that's what makes the water a little bit acidic. And this is not a super strong acid. It will make water acidic, but it's not going to make it terribly acidic. But this is the way in which Lewis acidity operates. Does that make sense? It's basically fulfilling its deficit in charge when it's stuck in water by pulling a hydroxide ion to it and leaving an excess of hydrogen ion. This is a Lewis acid, whether it's in water or not. You can interact BF3 with other stuff. It's done in organic chemistry all the time to make other kinds of chemical reactions happen. It's a Lewis acid either way, but when we stick it in water, it acts like a Bronsted acid. That's why I like to illustrate that. Now we go to ammonia and we see the opposite. Nitrogen is sitting over here in group 5, at least in the way I learned it, group 15, the way it's labeled on that chart. It's got 5 valence electrons. We park 3 hydrogens around it. It's got a full subshell, but it's got a lone pair, an extra pair of electrons that's not bonded to anything. And those electrons are basically unstable when we stick that into solution. They want to be shielded, and so it interacts with water by pulling a hydrogen ion to it to make ammonium, NH4 plus ions, and leaving behind a hydroxide. This is why when we bubble ammonia gas in the water, we get a solution that is basic. That's the way that the Lewis base acts in a Bronsted sense. So now we can broaden this out and think about, okay, what about all the metals, all the chemicals, the periodic chart, the non-metals, the metalloids, etc. And this can be done for the elements in any form, but the most common way is to look at them in their oxide form, right? Which is a typical form that you find a lot. If you're going to find, compound that's basically just a chemical element at the surface of the earth, is most likely to be oxides. Think about iron as iron oxide, rust deposits. And so we can divide up the chart into categories of elements that are basic when we stick them in water, and elements that are acidic when we stick them in water. And again, this is Lewis and acid basicity. These elements are acid and base as oxides, whether they are in water or not. They are Lewis acids and Lewis bases. But when we stick them in water, they become Bronsted acids and bases. And so it turns out that pretty much the bulk of the periodic chart from the metalloids over are basic when we stick them in water. That's basically everything, sort of all of this stuff. Each one are a little bit basic. And then we have the acid oxides, right? These are the ones that are way up here in the periodic chart. And the primary acid oxides are up here in this little cluster, right? Carbon, nitrogen, phosphorus, sulfur, silicon. These become a little bit less acidic as we go down. But these are the source of nitric acid, carbon dioxide, silicious acid, phosphoric acid, sulfuric acid. Even aluminum hydroxide is a weak acid, although that's officially in this kind of metalloid category. Even boric acid, BOH3, also a mild acid. And so this is part of the genesis of how, I guess the importance of electronegativity, which is an element's propensity to share electrons or not, and to pull electrons onto itself or not in the presence of other elements. In the presence of oxygen, these chemicals behave in a certain way that affects how they bind with oxygen, and therefore when we stick them in water, what are they going to dissociate into? Are they going to dissociate into a unit that leaves behind a hydroxide ion in solution, or a unit that leaves a hydrogen ion in solution, or neither? They're not going to really dissociate at all, in which case they have very little impact on acidity. And so it turns out that the basic oxides liberate hydroxide, more so if we're way over here than if we're kind of over here. There's a gradient. And the acid oxides liberate hydrogen ions. And again, they're not all the same. CO2 is a much weaker acid than sulfuric acid, for instance. So they do it, but to different degrees. So since we've already said that the CO2 system is the kind of fundamental thing on Earth that sets the kind of pH of waters at the surface of the planet, and then superimposed upon by the addition of various other kinds of acids and bases. It's useful to go through again what we mean by this, because I use these terms all the time in this semester. I just want to make sure that you remember them. You know, dissolved aqueous carbon dioxide is that, carbonic acid is that. Remember, this stuff is only fleetingly present. As soon as we dissolve CO2 in water, this stuff, carbonic acid, dissociates like almost instantaneously to make bicarbonate ion, HCO3 minus, which can also dissociate to make carbonate anion, CO3 2 minus. So especially the distinction between bicarb and carb are two important things to make sure you know the distinction of. And then on top of that, besides just taking gas and sticking it in water and making these various forms, because we have calcium carbonate solubility, we have sufficient calcium ions pretty much throughout the hydrologic cycle that some amount of calcium carbonate is going to form, okay? And so that is the combination of calcium and carbonate ions. Whenever we write out chemical equilibriums that involve solids either dissolving into or precipitating from water, they're always written, this is a convention, in the standard of the solubility. And it will be governed by a solubility style equilibrium constant, even though in the oceans, mostly what's happening is calcium plus bicarbonate is going in the back reaction to make calcium carbonate solids and to liberate some aqueous CO2 and some water. And you can write this equation in different ways. But the key point to remember is that to make calcium carbonate, your bicarbonate has to lose a hydrogen ion to turn into carbonate so it can make this molecule. So when this process happens, it liberates a little bit of hydrogen ion in the solution. And the way in this particular formulation, that hydrogen ion is consumed by taking, you know, basically 2 moles of this, turning one of them into this and one of them back into this, which then immediately converts back into this. And that's how you get this equation. But another simple way of thinking about it is that if you make calcium carbonate out of water, you're going to make the water a little bit acidic because you're pulling out a solid that excludes hydrogen ions from the starting product. So that has an effect on pH. And as you can imagine, this is a primarily biologically mediated process. It takes organisms. So whenever we have something in nature that requires organisms, we find that there are a lot of other variables that control how much something happens, right? Organisms need not, right, certain conditions to live, certain conditions of temperature and pH. They need nutrients. Photosynthesizing organisms need light. And so there are a lot of other parameters that will determine how much this reaction does or doesn't happen because it's involving organisms. Whereas all these other ones pretty much happen regardless, right? If you had an environment with a lot of respiring organisms, such as our cells, they could emit a lot of extra CO2, which could go into the water and acidify it slightly. So that is a thing as well, but not nearly as much as the way calcium carbonate affects pH in different environments. So let's look at what we call a Jerrum plot, BJERRUM. You may have seen one of these before in a chemistry class. They're used for acids and bases. They can be used for other chemicals besides acids and bases too, but we plot pH across the bottom, right? So basically 1 to 13, and I just made this plot. So sometimes you see them go 0 to 14, whatever. And this is the log of the activity of one of the chemicals involved for whatever acid base we're talking about. And so a log of an activity that is 0 means a value of 1, right? That's what log of 0 is. And what we're looking at is the variation in the parent acid, its first conjugate base, right? The first thing that it forms when it dissociates, and its second conjugate base. This is a diprotic acid. It's an acid that's got 2 protons, 2 hydrogen ions. If we had a monoprotic acid, we get a different diagram. If we had a triprotic acid, we would get a different like phosphoric acid, we have 3 of these crossover points. Okay, so you have to think through a little bit what's happening here. Low pH, basically, our acid is just undissociated for the most part. It doesn't like to break apart into other things until we get to a pH of around 5, right? Remember, that's kind of significant because that's this pH right here, right? The actual value is 4.8. It's just shifted slightly on all these diagrams because they're kind of shorthand notation. But if we reach 4.8, all of a sudden this concentration starts to go down. At the same time, this one goes up. And what you'll find is interesting is that the product of these two things, if you were to pull a value off, the product is going to be the same all the way throughout. It's just the relative proportion that is changing. And we, as you see here, we come down to a point where we're increasing in pH, where all of a sudden, boom, the amount on the blue line and the green line are the same. They're equal. And so we call the solution buffered here. And we'll go through what buffering is in a second again. But that's a buffering point, pH 6.35. If we continue raising our pH, we see that our carbonic acid just goes away, right? Because this is a log scale. Right? So the difference between 10 to the minus 2 and 10 to the minus 4 is already a factor of 100. So as this stuff starts going away, all of a sudden this carbonate ion starts to increase. And it comes up and it comes up, and then we get to this, what we call second endpoint, or other buffering situation at pH 10.3, where if we continue to raise the pH beyond that, we get to just pure or very high amounts of carbonate anions and less bicarbonate anions. Now this value is really high. We tend to not find it very often in nature. You can find some occasions, but for the most part, our natural environment, natural waters tend to sort of sit around this buffering point. They can go lower, they can go higher. Remember, seawater is up at about 8, which is somewhere up in the middle of this field. And so it's useful to have a mental picture of this diagram. In seawater at pH 8, if I ask you what is the most common ion in the carbonate system, you'd say bicarbonate. That's the one that's most abundant. These other ones are orders of magnitude less. If I said at pH 5, what is the most abundant material in the carbonate system, you'd say, oh, it's undissociated carbonic acid. Right? You still got a pretty big amount of bicarb, but the biggest line, the highest value is blue. Does that make sense? So I've also plotted on here the hydrogen ions and the hydroxide ion concentrations, just so you can see what they look like. But the important thing to recognize is that there's a couple of things that people talk about on these diagrams. Okay, they talk about these points, which are called endpoints, and that term comes from when people do titration and they're trying to get a solution to be at equal activity of acid and conjugate base, called endpoint. Solutions are maximally buffered at their endpoints. We'll go through the math in that in a second. And they are minimally buffered, and buffering is just how sensitive is a solution to adding additional acid or base. So in these places where they're buffered, it's pretty insensitive. You can add a little acid or base and not really change the pH. But you get to one of these other crossover points, they become very sensitive. Okay, they don't actually have a fancy term for them. They're just the sort of opposite of the endpoint. They're the place where the solution is most sensitive. So buffering is the ability to absorb acid or base and not change the pH substantially. So it only occurs in weak acids and bases. Strong acids and bases tend to not have any buffering capability. But a weak acid or base, which is something that can shift its equilibrium between being dissociated or non-dissociated as a function of the relative pH, will sort of migrate a little bit on either side of this buffering point. We have a little bit of base, we're going to go to a slightly higher pH. If we have a little bit of acid, we're going to go to a slightly lower pH. But we've got relatively similar proportions of acid and conjugate base. Whereas when we go to one of these anti-endpoints, the solution is very sensitive to adding acid or base because we have really different values. And so those are just little snips from this diagram. So I try to explain this with a simpler case, which is a monoprotic acid called acetic acid. acetic acid is found in household vinegar, right? So it's written out as CH3COOH. It's a common way of seeing it written. This is what's called a carboxylic acid. It can lose this hydrogen ion to make this thing, which is called a carboxylate anion. Okay, it's almost directly analogous to carbonic acid, right? The difference between carbonic acid and this is that we have, we don't have a second carbon in there. It's a much simpler molecule, but we can write out an analogous structure. So oftentimes for shorthand, rather than write all of this stuff out, I just write AC, which stands for acetate, CH3COO minus. And so this equation is basically saying HAC goes to H plus AC minus, which is basically just, like I say, shorthand. So if we write out the equilibrium constant, products over reactions, we take the minus log of both sides, minus log of the acid dissociation constant, and then minus log of the hydrogen ions. And I've already separated, I've done a little bit of math on here. I pulled this hydrogen ion out from this thing, but it's still minus the log of this. It should be plus, there's a missing plus on here, plus the log of these two things, right? And so if you can rearrange again, and I'll fix that to make sure that it's in there correctly. But we can pull this terminology, this term over to this side and come up with an expression that says pKa, which is just a minus log of the acid dissociation constant, minus the pH is minus the log of the ratio of the conjugate base to the acid. Right? That's all the AC minus the HAC ratio is. It's the ratio of carboxylate ions to acetic acid in this case. And so, excuse me, acetate anion, it's not carboxylate, acetate. So you can use this kind of really simple equation to think about what that means on those Jerem plots that I was showing you, right? That when we're at a buffering point, the pKa and the pH are equal, okay? That's what makes it a buffering point. And so this ratio becomes 1, right? And minus log of that is 0. So the difference, the offset between the pH and the pKa is 0 when we have a ratio of 1. Or vice versa, when this is 0, this ratio is 1. That's the whole gist of being buffered, is that when you're at one of these places where your pH equals your pKa, again, pKa minus log of the acid dissociation constant, you have equal values of, in that case, the blue and the green line. And so this is what a Jerem plot looks like for acetic acid. It's something I just made in Excel, where you can calculate out these values and then do a curve fit through them. I'll talk about this in a second. But this is basically a Jerem plot for a monoprotic acid. In the place where the pH equals the pKa comes out right here, and it's 4.8. 4.75 exact. So it turns out that acetic acid has an acid-base character that's very, very similar to carbonic acid. And it's useful to remember that because acetic acid is the simplest carboxylic organic acid that we know of, and it has a dissociation behavior very similar to CO2 system in water, which tells us that many organic acids, when we find them in the environment, are going to likewise, just like CO2, be in their conjugate base form. They're going to be ionized. And that ionization, that being as an anion, is an important part of their ability to complex and chelate other metals in solution. So then what about the fact that this solution is buffered? So I did a little calculation here. Okay, I'm going to add equal increments of base, small increments of base, and then calculate using the equation what happens to the pH. And so as we do that, as I keep adding a little bit of base, the pH is going down, and we reach a point where this is the ratio of A minus to HA. This is telling us the rate of change. So it's not the absolute value, it's the delta of the value. that occurs from adding the same amount of base all the way through. You see that as you approach this endpoint, adding in the same increment of base has less and less effect on pH. And so basically that's a kind of an illustration of bufferingness. But another way to think about it is just that bufferingness is this ratio. And when that ratio is 1, then we're at a pH equals pKa point. If we just take a little bit of acid or a little bit of base and we throw it into the solution, we're going to perturb this ratio a little bit, but the value is still close to 1. And that's why the closer we are to an endpoint or pH equals pKa point, when we add acid or base, we have less effect on the pH. It's just math. It's really just about the ratio. That's just another version of the plot in case you want to see. Okay, so pH is a function of the ratio of the conjugate base to the acid. But I know we like to think about pH as actually being minus the log of the activity of the hydrogen ion concentration, and it is totally that. But it is as much that as it is this, right? That just comes out of the math of what the acid dissociation constant looks like. Buffering is a solution where that ratio goes to 1 or is close to 1, in which case the minus log of that goes to 0, in which case the pH equals the pKa. So you will see me talking about pKa's a lot during the semester. Just remember, a pKa is all it is a mathematical function. It's the minus the log of the acid dissociation constant. And the reason we tend to think in those terms is because we tend to think in terms of pH instead of hydrogen ion concentrations when we talk about natural water. And for any acid, if its pH equals its pKa, and it has a similar characteristic to whatever the pH is in the water, then we know it's a buffered situation. We will find some acids have pKa's values that are really different than the carbonic acid system, and some of them are really similar to it. And that distinction is also going to become important. The relationship between this ratio and pH is going to be important for helping to predict the behavior of things in the environment. So when we deviate from a buffered point, we do it by either adding in hydrogen ions or adding in hydroxyl ions, which is like subtracting hydrogen ions. And we can shift away and, where we continue to pull stuff away, we can get to a place where the solution is least buffered. Okay. And finally, oxides of elements can be thought of as Lewis acids or Lewis bases. And again, these are going to help us to understand what happens in the hydrologic cycle as we start to weather the landscape and change the pH of water. So how is that? Is that all okay for everyone? Yeah, okay. So another term which is important is called alkalinity. You will see this like if you looked at your water quality report from the Board of Water Supplies, they'll have this term in there. I'm not a huge fan of it, but it's used commonly, and so it's useful to know what it is. Alkalinity is a fancy way of saying the sum of all titratable bases in solution that can be neutralized with strong acid. So you have a bunch of bases in solution that don't neutralize, and we don't count them. But you will find this, like I say, it's reported in drinking water, it's reported in wastewater, because it's a parameter that we want the alkalinity of water that, for instance, humans have perturbed in some way or another. Think about the wastewater that comes out of your house. We don't want it to be too dissimilar from the environment we're sticking it back into. So it's useful to know how alkalinity is defined. And for many waters, especially natural water, the primary control in alkalinity is to dissolve CO2. You can find some other things that affect alkalinity. We'll talk about them in a second, but the primary things are the amount of CO2 in solution. So the alkalinity, this is an equation, is approximately equal to, I'm saying approximate because I'm going to assume that it's all carbonate for this example. It's the activity of bicarbonate ions plus 2 times the activity of carbonate anions plus the amount of hydroxides plus the amount of, or minus the amount of hydrogen ions in the solution. And that is the total titratable base in a solution of just CO2 and water. So can anyone think why this one has a 2 by it? The carbonate anions? Because to neutralize it, you have to add 2 hydrogen ions. Just have to go back and look at the kind of stoichiometry of this reaction. To make this stuff, we add 1 hydrogen ion to it, we turn it into that. In which case, we got to add 2 to turn it back into that. It's still a base when it's this. So it requires 2 hydrogen ions to fully neutralize it. And so whenever you have any polyprotic acid conjugate base, meaning the ion that's produced from the dissociation of that, we got to add its stoichiometric coefficient to it for taking it all the way back to the neutral form. This is a total titratable or neutralizable base in solution. So if we started out a solution of neutral water, these things would be equal with each other, right? And they would just drop off. If someone told you, oh, I'm starting with water that's pH 8, right? Then we would know from our fancy math that we're going to have, more of this than this. The pH plus the pOH at 25 degrees C always equals 14, which means that the product of these two things always equals 10 to the minus 14. And if we have a pH of 8, then this one is 10 to the minus 8, and this one's 10 to the minus 6. And we have a pH of 9, that's 10 to the minus 9, and that's 10 to the minus 5. And then we have a pH of 4, that's 10 to the minus 4, and that one's 10 to the minus 10. And those numbers are all end up being pretty small and not having a huge effect on the alkalinity. Whereas the concentrations or activities of these things can have a much bigger effect. So depending on how much dissolved CO2 we have in the water, regardless of the pH, the alkalinity will go up the more stuff we have in solution. Because the more moles there are of something, then the more moles of acid or base we have to add to help with the neutralization. Now it turns out that in nature, in real settings, alkalinity includes other titratable bases besides those from the carbonate system. Some of the most common ones are borates and phosphates, right? So boron up there, phosphorus over here. These are common. And then organic acid anions, just think about the acetate anion in the example I just gave you. If we have ionized organic acids in their carboxylic acid form, they form a titratable base. And so we'll see this as a kind of really important parameter. If you go to places that are really organic rich, and a classic example that we like to talk about is the Amazon River. Amazon River, because there's so much biological activity in its watersheds, there's really high concentrations of organic carboxylic acids like acetic acid in solution. Most of those ionize because of what their pKa values are, and so therefore they become part of the titratable bases, which contributes to alkalinity. There's some other things too, some silicates, minerals can affect this. Like I say, that in contaminated waters, you can find all sorts of other things that contribute to the alkalinity. But the reality is that to a first order, the alkalinity is pretty much set by these things, right? Like I said, you can add a little bit of a subtle variation, especially due to boric acid. Like for instance, there's a fair amount of boric acid in the ocean, but it's going to be a fraction of the effects on alkalinity that come from CO2. All right, so now we'll start this next topic, which we'll continue on the next time, which is, okay, how do ions behave in water as a function of really simple things like, are they from electronegative elements or electropositive elements? How do they interact with the various things that we can find in water, the hydrogen ions, the hydroxide ions, the water molecules itself? And then we can kind of build up from there, and water has other stuff in it too. So we call the form of a chemical in an environment speciation. This is a chemistry term. So we can talk about the speciation of any chemical element in the periodic chart in its most common form as its speciation in water. So for instance, we talk all the time about sodium ions and potassium ions just being in there as sodium +1, that's its speciation. It's a +1 ion. Okay. And it turns out that the speciation or the form of an ion in water really is telling us something about how that ion interacts with water molecules and or the things that come from water, which are hydroxide ions and hydrogen ions. And you see here, if you notice, I've written out hydrogen ions instead of as H plus, but as H3O plus, because it's pretty rare to find free protons in solutions. If we have an acidic solution, the hydrogen ions are really going to be invisible, which is basically taking the polar end of water that has a negative partial charge on it, parking another hydrogen ion up against it, which means that the water is a lot less able to hydrate stuff, to park its negative end next to metals we talked about previously, because its negative end is busy neutralizing an extra positive charge. So the more acidic a solution, the less hydration we tend to find for our metals, all things being equal. Now, another thing that we can find in natural waters is dissolved oxygen, natural waters that are in equilibrium with the atmosphere, especially. And sometimes I write that as just DOX. That just stands for dissolved oxygen. And this can have an effect on the form a chemical takes in water, but not nearly as much as these things. But the key common similarity between all of them is the presence of oxygen. And in fact, the bond between oxygen and an ion, whether the bond forms or not, or what character that bond would have, for instance, is it acidic or is it basic? Is it covalent or is it ionic? All that kind of stuff affects the form that a chemical is going to take in water. So that's what affects the speciation. Okay, and furthermore, the solubility of the chemical, and there are trends throughout the chart, which I mentioned before. Things over here are really soluble, things over here are really soluble, things in the middle tend to be less soluble. It has to do with when the ion interacts with one of these things that has oxygen, what does it do? Does it make another ion that likes to stay in solution, or does it make a chemical that likes to come out of solution? And these things that are low in solubility are that way because the product of the ion interacting with oxygen makes something that's mildly ionic that tends to like to come out of solution. And we'll talk about how this works as we go. So this is a schematic way of looking at a metal X, just a metal with a charge N, right? So if it was sodium, X would be Na and N would be 1. If it's aluminum, then N would be 3, typically. And so we can write this out for a whole bunch of different elements. This positive charged ion is being hydrated by the polar negative ends of water, right? It's happy here in this situation. And in some cases, this is how it stays. Like in a case where X was really electropositive, really over here, really low in electronegativity, doesn't really want to make a bond. It's happy not being in a bond. It's got an ionic relationship with water. And so it's going to stay that way. And that's part of what contributes to those +1 and +2 ions in the alkaline metals and the alkaline earths, group 1 and 2, being so soluble in water. When we start to migrate over through the chart, think about carbon, which makes CO2 when we stick it in water. It tends to like to have a more covalent interaction here. There's a sharing, and that affects the way that the presence of that ion in solution is going to affect pH. We'll look at that next. If we continue going all the way over to this part of the chart, again, we find things that are negatively charged, fluorine, for instance. In that case, there's not going to be a plus charge, there's going to be a minus charge here, and waters are going to be flipped around, right? So that the positive charge will be sticking near the negatively charged thing. But again, we can think about how covalent that bonding interaction may or may not be to decide if we get a compound ion, which is from interaction with water, or we stay as a free ion. So the two parameters that decide that are the electronegativity, as I've talked about, and the size. So if you have like a really weird big ion, like these guys down here, right? they tend to have a different way that they interact with oxygen than something that's up in a similar period with a similar size to it. So it's not just the charge transfer aspect, it's also the size and shape of fitting stuff together. And these two things together really determine what kind of compound we're going to make in the presence of the products of oxygen dissociating in water when we stick them together. So the electronegativity is basically, as we've talked about before, just a measure of like, well, how electronegative, how much sharing is there going to be in a bond with oxygen? Is it going to be covalent, or is it going to be ionic, or somewhere in between? And hopefully you can already kind of see things that bond covalently with oxygen, which are things like carbon dioxide, SiO4, PO4, SO3. These are the common acids, NO3. So all these things that make really covalent bonds with oxygen, because they're close to it in the correct chart, they have very little electronegativity contrast, they make acids. They make compound ions in solution that are also acidic. And pretty much everything else in the periodic chart tends to be a basic oxide, and it tends to have a much less covalent interaction with oxygen. Again, the elements that are over here with less of an electronegativity contrast with oxygen are going to make a more covalent ionic interaction than the elements that are all the way over there. And that's part of what makes that distinction in solubility. These ones here that are neither super acidic or super basic as an oxide, they tend to stay as an oxide compound that doesn't dissociate in water, and that's why they're very insoluble. So the ion size is more of a fit thing, a size and shape relationship. And what really happens is the combination of the propensity of an ion to either want to gain an electron or give up an electron, as well as its size, together decide how it's going to behave in water. They merge together. And we'll see how they merge in a second. But I want to kind of illustrate how if we take a metal and we interact it with water, how that process happens. Remember, these metals tend to be Lewis acids. And what Lewis acids do, they're electron deficient. So in this case here, these little arrows are the flow of electrons. We can take a lone pair of electrons out of water and formulate a bond with metal X. And at the same time, because we can't have more than 8 valence electrons in our Lewis dot structure around water, we've got to liberate some electrons from one of these bonds. We're basically just trading a bond between oxygen and the metal for oxygen and hydrogen. So as this reaction progresses, we've made a bond here. We've lowered the oxidation state on X by 1, right? Because we added in some electrons, and we've liberated a hydrogen ion to solution, which basically shows up as an H3O+. That's an acid oxide. Right, all it's done is made itself a little bond, it's made a compound ion, and it's liberated hydrogen. So we can measure the ability or desire of an element to do that reaction. It can do it once, it can do it twice, it can do it as much as it wants, in something called ionic potential. An ionic potential has 2 parameters in it. It's got the charge on the ion and it's got the radius of the ion. And these are just 2 different formulations of it. And I apologize, it's a little bit confusing, but the axes are flipped. These are just from 2 different textbooks, but they show slightly different things. That's why I showed the both to you. And I color coded it to make it easy for you. The stuff up the middle is the same. It's the green field. Those are the elements that are right here in the middle of the chart. The ones that are not very soluble. Okay. The things over here in this kind of peach color, they're in this field over here, they're in this field over here. Remember, the axes are just flipped, but it's just charge and radius. Okay, those tend to be these elements over here. Okay, and the ones up here in this kind of blue-gray color, those are the ones that tend to be up in this part of the chart. And now you can kind of look at what it says on them, right? So here it says cations and octocations, plus charged things and plus charged things interacting with water. Here we have oxyanions. Oxyanions are things like phosphate ions, carbonate ions, nitrate ions, sulfate ions. And you'll see all of those things in this list. Arsenate ions, they're in the list. And then the things up the middle says oxycations, hydroxycations, and hydroxyanions. Cations and anions being plus charges, minus charges. The key thing about these things is that there's always going to be a little bit of this chemical that stays in water that's soluble, regardless of what form it's in. But this is just telling us what the name of it. And the fact that we can find both plus and minus charged circumstances in this central group, okay, tells us that they have a character that we sometimes refer to as amphoteric, which means when they are interacted with acid or base, they can flip what they do because they make a mildly covalent or a ionic bond that isn't super strong electronegativity contrast, and therefore they tend to make these kind of either plus or minus charged things, and that again contributes to them not being very soluble. And so we can basically take charge and radius and put them together into this term called ionic potential, okay? And it's listed here, and this is just a table of them, and I color-coded them again. The peachy color, the green color, the blue-gray color. These are a measure of charge over radius, and charge being Z, radius being R, okay? And the radius is in angstrom, so we drop out the 10 to the minus 8 that we would have if we were writing out radii in meters. And so you can kind of see what these values are. When they're less than about 3, we have low ionic potential, and we have our elements are in groups 1 and 2, plus some of the rare earth elements. Right? So group 1 and 2, low ionic potential, and rare earth, which are down at the bottom. And the high ionic potential elements are those things that are up there in the upper right, and then the stuff in the middle, which is a lot of periodic chart, is medium. So just remind yourself of all the stuff I've been talking about. High solubility, low solubility in water. So something about having a moderate value of ionic potential means that it makes it not very soluble. If you take it back to this diagram here, things with a very low ionic potential basically stay like this. They don't do this reaction. Things with a really high ionic potential do this reaction a lot. They do it, and then this does it again and again and again to the point that this becomes a negatively charged thing and has liberated a lot of acid in the solution. And that's again why we have these elements being acid oxides. And things that are somewhere in between, intermediate ionic potential, do this part way. They can do it typically to the point where they've neutralized N, and then we have a non-charged thing, and a non-charged thing tends to come out of water and not be very soluble. Let's see how we're doing on time. Okay, so this is a plot. I've shown it to you before, but I can remind you about it. That stuff on the extreme left and right in the periodic chart tend to be more soluble. Stuff in the center tends to be less. This is a log scale plot of the composition of seawater. And again, how soluble something is in pure water is not the be all end all. There are other parameters that affect what we see on this diagram, but part of what we see on this diagram, especially the very high values over here and over here, the tall bars, right, are due to this simple effect of how acid or base stuff is. And I think I will, there's 2 more slides. I'll throw them in next time so that, you know, we can finish on time today. And we will continue this discussion about solubility. The next thing we're going to do is add some other stuff into the water besides just pure water. Right, and then you'll see how what kind of modifications it can have. And one of the main thrusts is that we can add stuff to water that increases the solubility of this stuff in the middle. This stuff on either side doesn't really need any help. And there's very few things we can add to the water that lower their solubility, but there are things that we can add to water to make these sparingly soluble things with intermediate ionic potential become more soluble. All right, are there questions?
At this point, I imagine I will have